Hi, I'm Brandon Graisley. I'm a high school math teacher. This is the second video for geometry, this one dealing with polygons. And we're going to look at what you already know about polygons here. This particular one, the triangle. You know that the angles on the interior, the inside angles in a triangle, always add up to 180 degrees. So this isn't exactly to scale, but imagining this was 75 degrees, and this was 60 degrees, and we didn't know this value, the angle A in this corner, then we know that A plus 60 degrees plus 75 degrees must be equal to 180 degrees, and you can solve that to see that A must be equal to 45 degrees. So that's something that you have known from the past, I'm hoping. We're going to continue to use it. We have this triangle here. Let's say there's 20 degrees up in this corner, and the angles down in these corners are the same. They're both some unknown value x. We can use the same logic. 20 plus x equals 180 degrees. And we can solve that in a few ways, but 20 plus 2x equals 180. That is 2x equals 160. Dividing both sides by 2, x equals 80 degrees. Now some people might think of this like, oh, there's 180, take away the 20, there's 160 left, I'll divide it equally into the two sides, without doing all of the equation stuff, which is fine as a good way to think about it. If you need to show your work and explain what you're doing, this is a good quick way to do that. And we also know that some triangles aren't possible. For example, here's a triangle. There's 95 degrees right there. There's 102 degrees right there, and we have some unknown side here. Well, if you try to work this out, these two sides together, these two corners, these angles, add up to more than 180 degrees, so there isn't even room to fit some non-negative x value here, some positive x value. So this triangle can't happen. It's not possible. These don't exist. So that's stuff that you hopefully already know from the past. Triangles, the interior angles add up to 180. Now let's look at a rectangle with 90-degree angles in the corners here. I'll write them all in. We don't typically. And we can see 1, 2, 3, 4 of those. 4 times 90 degrees is 360 degrees. That's the sum of the angles on the interior of a rectangle. And the question came up in class, is that true for other kinds of quadrilaterals? And so I'm going to show you that it is. Here's a wacky quadrilateral. It's nothing in particular. It's not a parallelogram or a trapezoid or anything like that. And we have these interior angles, 1, 2, 3, 4 of them, but it's not clear what any of them are. So as a strategy here, we're going to divide this into two pieces, each of which is a triangle. And so you see 1, 2, 3 angles there. Those ones must add up to 180. And then 1, 2, 3 more over here add up to 180. Now you notice I drew these really carefully. That together, those two angles add up to this one larger angle from the quadrilateral, and same with down here. So 1, 2, 3, 4 angles altogether must add up to 360 degrees. And so that is true for all quadrilaterals, which is pretty nice. It's even true, these are called convex quadrilaterals, but it's even true for some other wackier ones like this, where there's sort of a dent in here. If you add up these angles, 1, 2, 3, and this one on the outside, this is on the inside, but it happens to be a reflex angle, they still add up to 360 degrees, and you can show that by just making a triangle out of it like that, making two triangles. So quadrilaterals, four-sided polygons, always have an interior angle sum of 360 degrees. So let's ramp this up and look at what happens as we get larger and larger polygons with more and more sides. So let's go to a pentagon like that. Sorry about the curve there. There's a pentagon, and we're going to do the same strategy of just dividing it like this. And actually I've got a quadrilateral and a triangle right now, so we could stop right there if we want. 180 plus 360 for the interior angle sums. So that's going to be a total of 540 degrees. Now the other way, if you don't want to use the thing we know about quadrilaterals. You can just use triangles. Pick a spot and divide up anything that's not a triangle into triangles. 1, 2, 3 triangles. Each is 180 degrees. And so 3 times 180 degrees is 540 degrees. And this we can generalize up. Every time we add a side, we end up adding a triangle. So in general, you take the number of sides, take away 2, and multiply that by 180 degrees. So let's just try that out with our examples. With a triangle, we would have 3 minus 2 times 180 degrees. That's 1 times 180 is 180. With a quadrilateral, we would have 4 minus 2, 4 sides, subtracting the number 2, times 180. That's 2 times 180, or 360. And every time we add a side, three times 180. Every time we add a side, we are adding on 180 degrees. We are adding on one additional triangle. So that's pretty nice. And then we can use this idea of dividing a polygon up into its pieces like this. We can use this to predict the interior angle sum of any polygon, even if it has a bazillion sides. Like here's one with blah, 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 blah. Let's say it has 20 sides. We would take 20 and subtract 2 and multiply by 180 degrees. That would be, let me just write this out a little more, that would be 18 times 180 degrees, which is 3,240 degrees. That's how much you would get by adding up all of these little interior angles all the way around a 20-sided polygon. Okay. Now that's the inside of a polygon. What happens on the outside? So here is a triangle. We know about the inside, adding up to 180. Let me use a specific triangle. Let's go 60 degrees, 70 degrees. That's 130. That means this must be 50 to add up to 180. So there's my insides of my triangle. Now imagine you're walking along, these are like 3 streets here, and you're walking along this street in this direction, and you come to this intersection, and you decide to make a turn. You decide to turn this way and continue walking along this side of the street. So walking here, and you turn according to my arrow, and you travel this way. And you do the same thing at all these corners. Here you come back like that, you continue walking along this triangle here, and instead of walking straight, you're going to make this turn and continue back along the way that you came. So walking 1, 2, 3 sides of the perimeter of this triangle. When you do that, let's see, 70, this is a straight angle here, so this must be 110 on this side. Over here, that's 60, that makes this 120 degrees, straight angle, 60, 120. And then this one over here, straight angle, there's 50. This one over here must be 130 degrees. Now if you take those 3 values, they always add up to 360 degrees. And if you think for a moment about what that means is you were facing this way, which is sort of, what's that, northeast on this diagram here. And what you did as you walked around this block is you made a full turn. You walked all the way around once, and you've ended up facing the original way that you started off. You were facing to the northeast, and as you walked around, you made a full turn by walking the perimeter of this triangle. And that will be true with any shape. It doesn't matter how many sides it has. If you start in any particular spot and you measure this angle here, take the straight angle and make your turn onto the next side. If you add up all of those, it will always add up to 360 degrees. And that's called the exterior angle theorem. Add up all those little guys, 360 on the outside. It's not the entire reflex angle around the outside here. That's totally different. Just this one little short bit off the straight angle, and that's the exterior angle theorem. Okay, so that is all I needed to tell you for today. I hope that is good, and if it is not, please let me know in the comments. Thanks.